In 8.3, we're still looking at the differences between means. The key difference here is that we have dependent samples, which means that for each item in the first sample, it's paired up or matched precisely with a corresponding item in the second sample. This was first mentioned back in 8.1, and there's a little graphic here. With independent samples, the sample sizes can be different because um, there's no restrictions here, but with dependent samples, there has to be the same sample size in both of your samples, and there's a pairing, a connection between the data in the first sample and the data in the second sample. Every item is matched up with a corresponding item. The overall concept is still the same. We expect our null hypothesis is that our two samples are not going to have any difference. And then we're going to see and look for a difference. And if it's really large, really far out in the tails, we'll end up rejecting the null hypothesis. So a couple of key things we'll have to calculate with these dependent samples is D bar and then SD here, the mean of the difference between the paired data entries and the dependent samples. So just how far apart, subtraction here, those paired items, how far apart are they? Add them all up, divide by how many are there, how many of them there are, the mean. And then the standard deviation of the differences between the paired data entries. So we're going to use that value then perform this calculation. So let's jump into a problem and I'll show all that. A scientist claims that pneumonia causes weight loss in mice, and this is number 7 here of the review homework. The table shows the weight in grams of 6 mice before infection and 2 days after infection. So you can see how this is paired data here. It's the same exact mouse before the infection and after the infection. So there's a clear relationship there. 6 items in our before sample and those same 6 mice in the after they get infected sample. We have our alpha. Is there enough evidence to support the scientist's claim? All right, so we have to identify our null and our alternative. In this case, our null, our claim really here is that there's weight loss in mice. And so that's going to give us our alternative here that the difference is going to be greater than 0. So if you think about that, if we're assuming our second sample is smaller than the first because the mice have lost weight, the numbers have gone down, then when you subtract those numbers, you get the difference between the samples. The first value minus the second one is going to be positive because the second numbers are smaller because the mice have lost weight. So that's why we're getting that the difference between our sample values is greater than 0. And so then our null, it has the equality in it, and it's less than or equal to 0. So we copy the data here into Excel. The first thing we want to figure out is the actual difference. So all I've done is subtract the mouse's weight before he was infected and then after. So do that for each of them and you get the differences between all of our paired data. And then our test statistic here is just the average of those. So you could just use the average function. That might be easier. I summed them up and divided by 6. But yeah, the average function, should have thought of that first. That's going to give you the same exact result because we're averaging the differences. And so what we want to do then next is I'm going to work to get this standard deviation here of our differences. And I'm going to need these columns here to calculate that. So after I've had this test statistic, I want to take each difference and subtract away the test statistic. And so I'm showing here with all the decimal spots out a little bit further. You want to have at least, if you type in these values, you want to have at least 4 to 5 digits of accuracy. The more the better. So I was just showing there that my value actually is 0.95, that there's no hidden decimals from rounding. So I could type 0.95 here. I want to do the difference minus 0.95 minus that test statistic. You can still use cell reference, but you need to put a dollar sign there so you can drag it down then. And each time it'll stay on F4. If you don't have the dollar sign, it would go to F5, F6, F7, and so on. But when you put the dollar sign in, it kind of locks in that number that comes after the dollar sign. So it keeps referencing, it keeps referencing that same cell even after you've done the drag down. So let me get rid of all those extra decimals since they're not necessary. But you do your difference minus your test statistic. And then you want to square those results. So I'm just taking this value squared, then that value squared, and that value squared, and so on. So square them all. And then finally, you want to sum up all of those squares. And after we've summed all the squares up, we can come down here. I want to take that sum and divide by my degrees of freedom, which I haven't mentioned it yet, but degrees of freedom is the standard. It's just one less than our sample size. So in this case, it's going to be 5 because there were 6 mice in our sample. So what have I done? We've done this formula here for that standard deviation. Or I took each, trying to get it all on the screen here. I took each difference and subtracted away the average of the differences. So the difference here, subtract away the average. And then I squared all those values. Squared them all. And then finally you sum up all of those squares. And then to get your final result, we're going to take the square root of that sum divided by the degrees of freedom. So that's the main bulk of the work for these type of problems, because after that, the rest of it should be pretty familiar, or similar at least. The alpha here, whatever it is, you can get the rejection region. We're using the t-distribution. And since I just have a one-tailed test, I just want that 1 to know what the critical value is for that 1%. I don't need to divide it by 2. And you type in your degrees of freedom then, which is again 1 less than the sample size. So that is my critical value. If I get a test statistic that's further away from 0, further into the tails, then that I'm going to reject the null. Reminder, this always gives you the left side critical value. Since I am looking for a greater than 0, a right tail test, it would just be positive 3.365. That's my positive end critical value. And my test statistic comes back greater than that. So it's further into the tail, so I will end up rejecting my null. And just to see how to calculate the test statistic, it's going to our standardized test statistic, this looks kind of familiar. It's our value we get from our samples, and then minus our population difference here, which we're most likely all the time assuming it's 0, that they're the same. So we're subtracting 0, and then divide by that standard deviation we calculated, but also divide that by the square root of n. So this is the formula I'm going to work here. And let me copy that over so you can just refer to it as I talk through it. So we take our difference value, our test statistic that we figured out early on here, and we're subtracting 0 because that's what our null is that there's no difference between the two samples. So that's what goes on top. And then we divide by the standard deviation for the test statistic that we figured out here. But you also need to divide by the square root of your sample size. So type all that in, you do that, and that's how you get your test statistic for your particular samples. And like I mentioned, this is further in the tail than our critical value here, so we're going to end up rejecting the null. And in 8.4, we're looking at proportions. We're going to assume that each of our populations are the same, which means we would assume that our samples would have similar proportions. So if we get our samples and they're really far off from each other, really far out in the tails, then we'll reject our null hypothesis that our population proportions are the same. So looking at number 9 here from the review homework, in a survey of 210 males, it gives us the proportion who were enrolled in college. In a survey of 250 females, it gives us the proportion who were enrolled in colleges. We have our alpha, and we're trying to decide if the proportion of males is less than the proportion of females. So that's our alternative here, that the male proportion is less than the female proportion. So that's our null then would have to have the greater than or equal to for the proportions. Critical values with proportions, we're dealing with a normal distribution. So with alpha being 0.10, 10%, you just do norm.s.inverse with that 0.10. And we are doing a left-tailed test, so that negative, we want that negative value for our critical value. And then we find our standardized test statistic, which I'll show you guys how to do. And if this was further away from 0, then we would end up rejecting our null hypothesis. Since it comes back closer to 0 than our critical value, we fail to reject the null. So what you have is your two samples, and the problems could be presented to you a little bit different. This problem gave us the sample proportions, so we knew how many there were and the sample proportions, how many total there were in the sample and the proportions. You also want to know how many fit the criteria within each sample. So 35% of 210 gives us this value, and 38% of 250 gives us this value here for our females. So the problem could just give you the how many, or it could give you the proportion already. Either way, you should be able to get all three of these values, because it'll give you 2 out of the 3. So then our estimate for the population proportion, we have to do that first. So we want to add up the two amounts from each sample that came back, in this case enrolled in college. So add those together and then divide by how many total people there were all together. So we do that, and you'll notice this value is always going to be in between your two sample proportions, because it's kind of like averaging out those two samples. So we're right there in between our two sample proportions. If we combine everybody together, this is the proportion of people enrolled in college. And then just do 1 minus that answer to get your Q. And so our standard deviation for the test statistic is this big part on the bottom. I like to calculate that first rather than type everything in at once. So you use that P and the Q that you just calculated right here, and then you multiply by 1 over our sample size plus 1 over our second sample size, square root of all that. So square root, those two values multiplied together, times 1 over that plus 1 over that. So square root of all that gives us the bottom part here, and then for our test statistic, we do our sample proportions to track each other. Let's see how far apart they are. And we're assuming it's 0. That was our initial assumption. So this part is 0 again. We're assuming our populations are the same. So I just subtract our individual sample proportions and then divide by that standard deviation piece I just found. And that gives me the standardized test statistic for our samples. And like I mentioned, this value is not as far away from 0 as our critical value, so we do not reject our null.